I work with SITELLE data, and I'm going to present the last results we obtained on the Crab Nebula. So the Crab Nebula, as most of you know, is a supernova remnant, which comes from a supernova which exploded in 1054. It's up to a few years ago. It was one of the most studied objects in astrophysics, but still we don't know the origin of this remnant, and especially if the question of the explosion, is it a low energy explosion or high energy explosion, or typical high energy explosion? The problems come from the fact that we indeed observed the Crab Nebula, the explosion of the Crab Nebula in 1054. So it makes it, in principle, a high energy supernova. But when we look at the remnant today, we can see that if we measure the kinetic energy of the remnant today, the kinetic energy is 10 times lower than than the energy which would have been our input by a high energy supernova. One of an hypothesis by Nathan Smith in 2013 is that this is indeed a low energy supernova, but it exploded, the star exploded in a cocoon of circumstellar material, which has been ejected by the previous stages of the evolution of the star. The question remains, do we have any proof of the presence of circumstellar material around the star? Our last paper, which is still to be published, in this paper, we compared images taken by megacam at 3 different epochs to reconstruct the whole the proper motion of the Crab Nebula, so the expansion of the Crab Nebula everywhere on the nebula. And one interesting result was the fact that we could see in blue on the right, this is an acceleration map, so this is the acceleration of the material, and we can see some blue decelerated parts in the remnant, which might pinpoint to the presence of circumstellar material. The problem with images is that we cannot disentangle the proper motion of every filaments, because there are a lot of components along the line of sight, first, and second, there's a high continuum which comes from the pulsar wide nebula, which is very difficult to remove. So we use SITELLE. We already had obtained in 2016 a cube of the Crab Nebula, which helped us reconstruct the whole nebula in 3D. And we took a second cube in 2022. I don't know if you can see it, but the old cube is in blue and the new cube is in orange, both in velocity space. And you can see, well, I can see the fact that it's indeed expanding. Okay, the orange part is on the outer skirt, while the blue part is in the inner nebula. So that opens the possibility to measure the proper motion, but in the velocity space this time, filtering by velocity. So we just have to make slices of velocities and compare the velocity slices at different epochs. So in 2016 and 2022, the SNR in 2022 is much better. But you can see that there's a little expansion which can be measured. We built a convolutional neural network to do this measurement with the help of Penelope Glassman. And we obtained everywhere in the nebula for the first time the 3D velocity. So the proper motion everywhere, plus the radial velocity, which is directly obtained with SITELLE. So that's the first ever and unique map of the 3D velocity of an astronomical object and of a supernova remnant. Just to so that's the results we obtained with MegaCam, and if I project back the data we obtained with SITELLE, we obtain that. Okay, so it's the results are much clearer, certainly because of the use of CNN, but also because we are able to disentangle the different velocity components from the line of sight, and we are able with SITELLE to remove completely the continuum, which moves completely independently of the filaments. So we have been able to go further, and as we have the S2 lines, we can compute the density, and from the density we get the mass, and as we also have the acceleration, we can compute the force. Okay, so this is the map of the mean force applied on every pixel during the last 1,000 years. And you can see that there are regions in blue here are decelerated regions where the force is negative. It's the mean force. We don't know how it was distributed during this time, but we can compute the mean. Problem is, it's not a well-defined, let's say, a torus of a decelerated material. It's much more complex than that. In fact, there are decelerated regions everywhere around the nebula. But when we compare these results with older data, like for example here it's the continuum map of the pulsar-wide nebula, so you cannot see the filaments. It's just the cloud produced by the pulsar-wide. You can see some indentations here everywhere around the nebula, which are believed from a certain time to be the result of the presence of circumstellar material. And when we superimpose our data to that, we can see that the regions on the outskirts where we see a lot of decelerated material are indeed related to dispositions of the dark base. So this gives clue to the possibility of the presence of CSM, which would maybe help answer the question of the origin of the Crown Nebula. Some signals, it's related, but not completely to the proper motion. It's not related to proper motion. We just also, by the way, have the distribution of mass in 3D of the remnant for the first time. Also, it's the first time we can get this kind of data on a supernova remnant, and we can see that it's highly anisotropic. There are much more mass in the north part than in the south, and it likely originates from the fact that the explosion took place not in the very center of the star, but just but just at but near the center, not exactly. And this could generate highly anisotropic distribution of material. That's it. So, but in conclusion, we get a lot of new data which are still to be analyzed. We still uncertain, but we have much more clues on the origin of the Crown Nebula now. And this gives a lot of fuel for supernova explosion simulation, since we have already, nowadays we have 3D simulation. But we still have, in general, 2D data. So now, for the first time, we have 3D data to put in the simulation. That's it. Thank you.
Any questions for Thomas?
What is the ground shears on spatial velocity structure?
Oh, it's
the questions. Wow.
Spatial, yes. So this the ground truth. We compared this data with the data we obtained with MegaCam in 2D. Okay. So and it's just better. We have a better resolution, but it gives the same kind of results. Okay. Yeah. I don't know if I'm not sure I answered your question.
It just seems that your head is some translation to get 3D conceptuals that, and I'm curious to know if you have to demonstrating the technique is successful. some of the way.
If we, for example, we use, it doesn't completely answer the question, but we use the 6 differently trained CNNs to check for uncertainties, because one of the major problems with CNN is the fact that you have one estimate, and doing that, we cleared the problem of out-of-domain errors, for example, and we get very good uncertainties on this. I also simulate data to check its semi-synthetic. It was trained on semi-synthetic data, so it really works well with semi-synthetic data. But the use of 6 differently trained CNNs helps make sure that it's not completely it's not an hallucination of the CNN.
Any other question? Yes, please.
So,
Just to wait. But
story on the giants was like this.
can you repeat the questions?
Other improvements and usages are original.
Yes, it's the hypothesis of Nathan Smith. In fact, the idea is that, yes, that's true. Went fast on that. The idea of Nathan Smith is that the presence of the cocoon of circumstellar material this cocoon was lightened up, in fact, during the explosion, which elevate the brightness of the explosion at this time, in 1054, to the brightness of a typical supernova explosion. But it might not be the case. In fact, it could be a low kinetic energy supernova.
Okay, I think if there's no more question, let's thank our speaker again.